Hello everyone, thanks for coming back to class. So today's lecture topic is graph partitioning. So graph partitioning is the split of a graph input into subgraphs by partitioning its set of nodes into mutually exclusive groups. So assume that we have this input graph data. So just intuitively, we see there is 3 graph partitions, right? So let's say each group should be mutually exclusive, which means when we get the partition from the whole graph data, so each partition is interconnected, more and densely interconnected each other. So compared to the other partitions, so I mean they have more inter edges within the partition compared to this cross edges between the partitions. So I would say I will introduce mathematical measures to define how similar they are. So the graph partitioning is the exact solution, an NP-hard problem. So there are 2 to the n minus 1 power minus 1 ways for getting the distinct cuts. So when we divide the network into the 2 groups, so in that case, so we have these possibilities. And this is the combinatorial optimization problem. So we need to define the optimization criterion, and we need to choose optimization method. So we will talk about several popular optimization criterion and method in this lecture. It could be solved by greedy and approximate algorithms or heuristics because it is an NP-hard problem. But we have these sort of the methods. And the result-wise, it could be balanced or unbalanced partitions. So we will talk about the proposed solution is likely to be balanced or unbalanced. And depending on method, so we can just get the 2 partitions from the input, and we can get multi-way partitions for the input. So we will talk about these perspectives today. With respect to the optimization criterion, so we assume that the graph input is partitioned into 2 set of vertices, 2 set of vertices, and we can suggest 4 possible criterions. So these are some most popular criterions and not all the criterions. So to divide the graph input, so we can minimize the graph cut. For example, so when we have, for example, these graph input, so we define these are the V1 and V2. So we have this is the cut. So mathematically, when we have these 2 sets, so we may imagine many different numbers of the partitions to assume that these are the candidates. From these candidates, that these are input candidates, so these came to the cut function. So cut function just count between 2 partitions how many edges we have. So in this case, we have just one edge, and we have just one. So we can minimize the cut, and so intuitively, the partition, we assume that each partition is the mutually exclusive, right? So they have more intercluster, and we have likely to have less the intercluster, right? So we try to minimize the number of these interpartition edges. So this could be the one of the criteria. So we try to minimize the graph cut, right? But sometimes it is not fair to just count the number of the graph cuts, right? Depending on the size of the V1 and V2, relatively it is very small, but when we just count and it doesn't reflect the actual the graph structures, right? That's all we need to consider the size of the partition 1 and partition 2, right? We normalize using the number of vertices in the V1 and V2, and then we summate. We try to minimize the ratio cut. Sorry, it should be ratio cut. And we normalize the cut in different ways, right? So we have another normalized cut using the volume. The volume is just considering the vertex, the edges within the V1. So I'm sorry. So it is from the V1 to all the other vertices. So from the EIJ, so I is from the V1, the J is from the entire vertex, the vertices, right? So we get this information. So this is actually the same as the sum of the node degree. So Ki is the degree of the node I. So we use this, the edge-wise information, we get the normalized cut. So quotient cut, we also say the conductance is minimized, considering the minimum value of the volume of V1 and volume of V2. So these are the popular criteria. They all try to minimize. So let me start with the easiest one. So the Kyger's algorithm was proposed in 1993, so quite old algorithm, but very simple and intuitive. So Kyger algorithm is the randomized algorithm to compute a minimum cut of a connected graph. And this figure shows the example. So the result of the output of the Kyger algorithm may produce these partitions. In this case, this line gives the cut, and otherwise we get these one produced, for example. So in this case, the Kyger algorithm find this as the cut. So you will find, and basically you randomly choose the edges and merge the connected nodes to the one, and we contract the graph data, and iteratively we contracting the nodes until they find the minimum cut. So we'll give you more example. So the idea of algorithm is based on the concept of contraction of an edge, in the graph input. So the contraction of an edge merges the node into the one. So for example, so when we contract this edge, AB, after the contraction, we have just one node. So let's say this is AB because it's contracted into just one node from the two nodes which are connected by an edge. So we randomly choose this edge. We contract this relationship into the one. So all other edges connecting either so U and V. So assume that let's say U and V, and so we have I is here. So when we select this edge and contract the edge into the one node to make one node, and the remaining edge is connected to reattached to the merged node. So after contraction, so we have U, V, and I, right? So previously it has the edge between U and I, and we still have the edge between U, V, and I, and we have another edge toward the V, and we also have this edge. So in this sentence, I explained the reattaching to the merged node. And Kargar's basic algorithm iteratively contracts the randomly chosen edges till only two nodes remain. So for example, we have many edges, and we contract the edges, and we iterate the contraction procedures until we have just two nodes are left. So by iterating this basic algorithm a sufficient number of times, the minimum cut can be found with high probability. So we just rely on high probability. So that's why it is called the randomization algorithm. But we expect much better than just randomly choose the partition. So we just expect the probability to find the minimum cut is better than the just random choice. So we give you another notation. So we have E. So the jerk of contracting the edge is the new node UV. So it was UV and it becomes UV right now. So contracted nodes U and V with all their incident edges are removed. The result of contracting edge E is denoted as G / E. The construction algorithm repeatedly contracts random edges in the graph until only two nodes remain once again. So at which point there is only a single cut. The key idea of the algorithm is that it is far more likely for non-mean cut edges than the mean cut edges to be randomly selected and lost to construction. Since the mean cut edges are usually vastly outnumbered by non-mean cut edges. So this is example. So looks like a, so this is the ground truth. So we have two partitions, and we expect the Kaggle algorithm is able to find the partition and then the min cut edges. So the randomly choose this, we expect the edge is not the min cut edge, and we contract the edge and created one node, and we choose another one, and we get this, which is randomly get another one in contraction, choose contraction, and choose contraction, and choose contraction, and we are able to find this. So in this case, min cut size is the 3. So these are results, and this is the formal procedure. We have the construct function. It gets the graph input, so it iterates until we have the number of vertices is more than 2. We choose the E uniformly at random and contract. When the number of vertices is 2, we return the cut. So probability of the final cut is equal to the mean cut is more than 2 over n squared. So n is the number of vertices, but still better than just randomly choose the partitions. So it run to omega of n squared times and choose the smallest cut. So this was the beginning, and now we move on to a more advanced algorithm. So we slowly toward the one of the popular partitioning algorithm, so which is called the spectral clustering and spectral partitioning, sometimes we call. Let me introduce more notations to understand the graph cut. So to represent the graph cut, we can give you the newly introduced indicator vector. So once again, we are interested in finding two partitions. Let's say V is composed of V plus and V minus. So assume that we have two partitions. The indicator vector is composed of -1 or +1 or -1. So it is able to find just two values, the indicator vector, and it has a V number of the integer value. Assume that we have 5 vertices, so it can have this -1 or +1. So indicator vector means it is able to represent the partition ID. So our goal is to find this indicator vector. When we are able to find the indicator vector, you can get the partition. So by looking at this, the indicator vector. So indicator vector is like a ID, so identifier. So by looking at just the integer, we just identify the two partitions. So by looking at -1, +1 nodes, and the definition is here, right? So if the node I is the part of the V plus, we just give +1 or -1. So which means we try to develop an algorithm to return this SI. And we expect the resulting partition satisfies the previous optimization criterion. For example, the graph mean cut, or ratio cut, or conductance, and normalized cut, right? We'll come back later. So here we start with the graph cut, but we haven't introduced cut yet. So now we have the cut here, and cut is could be defined this. So it should be considered only if they have edge between the v plus and the v minus, and to make it the same, and we need to do 1/4, and so start with the definition, and we can develop more. So instead of this notation, we can introduce the adjacency matrix, and we still have this. Because S could be the +1 and -1, and we can easily see this is the same as this. And we also introduce Ki. The new notation is the degree of node I, and delta ij becomes 1 if I is equal to j, and otherwise 0. It could be simplified this, considering this. And we can simplify once again like this. So by this observation, this is same as actually the degree matrix. So as you know, degree matrix is a diagonal matrix. So in this case, it has the degree of the each node. So for example, at the first position, so we have the degree of the first node is placed in here, and A is adjacency. So we are able to get this cut matrix. And then, so graph cut is could be defined using Laplacian. So we have talked about Laplacian, right? So when we talk about the graph neural networks, so Laplacian matrix is computed from the D minus A. The D is diagonal the degree matrix. A is adjacency, and their computation is like this. And in this input, we have something like this operation.